topic for today is about subgroup test. But before anything else, let us briefly recall what a subgroup is. A subgroup is a subset of a group that is itself a group under the same operation. If H is a subgroup of G, we write H less than or equal to G. Okay, before we delve into our new topic, let us read our learning objective. At the end of the lesson, the learner should be able to first differentiate among the one-step subgroup test, two-step subgroup test, and finite subgroup test. Second, show appreciation for the efficiency of subgroup test in simplifying mathematical proofs. Now let us start with one-step subgroup test. The one-step subgroup test states that if G is a subgroup of H is a non-empty subset of G, and if for all element AB inverse is also in H, then H is a subgroup of G. So in this test, we only check two things. First, H must be not. The second method is the two-step subgroup test, H must be closed more intuitive because it follows the definition of a group more condition already. First, the set must be non-empty closure and existence of closure. Meaning why it is the product one-step test two elements because closure and inverse belong verified together in one. Finally, we check the inverse property, meaning every element must have its inverse inside the set. If both closure and inverses are satisfied, then the set is a subgroup. For instance, the set 1 and -1 under multiplication forms a subgroup because element stays within the set and each element is its own inverse. The third method is the finite subgroup test. This applies when a subset has a finite number of elements. In this case, the process becomes simpler. We only need to verify that the set is non-empty and closed under the operation. If these conditions are satisfied, the existence of inverses automatically follows due to the finite nature of the set. So, for instance, the set 1i, -1, and -i under multiplication is finite and closed. So it must be a subgroup without separately checking inverses. Finally, to show that a set is not a subgroup, we only need a single counter example. If here it is. If any group property fails, then the subset cannot be a subgroup. The easiest property to test is closure. For example, the set of irrational numbers under multiplication is not a subgroup because multiplying the square root of 2 by square root of 2 it gives 2, which is rational and therefore not in the set. Since closure fails the set, it is not a subgroup. So in summary, subgroup tests provide efficient ways to determine whether a subset forms a subgroup. The one-step test check A and B inverse, and the two-step test checks closure and inverses separately, and the finite test requires only closure for finite set. If counterexample exists, the set is not a subgroup. So this method simplifies the verification process and makes studying algebraic structure more manageable.